Okay, so what happens to the electrostatic pressure going from a voltage of -1 to 0? So let's do -1 to 0 will be part A, okay? Going from -1 to 0. Well, we can say that the electrostatic pressure is neutral, gone. That's easy to understand, right? It's like at this point, there is zero pressure on the rubber band at all. So there's no need for it to try to get back to any point because it is neutral. That's easy. Now, B. Now we're going from zero, neutral, to +1. This is key. First, the EP returns, but it's in the opposite direction. Because remember, what does the voltage mean? What is it referring to, and where do we measure the voltage? We're measuring the voltage from inside our. I missed. This happens all the time, by the way, in these experiments. I can't tell you how many times the electrode boop pokes right through, and you've ruined the neuron, and you get made fun of. But you learn. We're measuring from inside the cell. So what we're saying is inside the cell is now positive. Inside the cell has become positive. So now that we're positive inside, things are very different. This is what the situation was when we were negative inside the cell. Right? Negative inside the cell. Now, ah, now we're saying we've become positive inside the cell. And this is the situation. So here's what changed. And now I'm, of course, noticing that I forgot to change the CL. Of course, electrostatic pressure is the same irrespective of what we're talking about, so it affects all charged particles. But the reason I had left this out was because remember, chloride is not really significant to us. So what changed is now we're positive, positive, positive. The inside of the cell is positive, the outside of the cell is negative. Now that we're positive inside, what kind of particles do we want? Positive or negative inside? Of course, we want negative. We don't want these because we're positive. And just for completeness, now that we're negative outside, do we want positive ions or negative ions? Of course, we want positive ions out here. Opposites attract. So let's look at what happened. The arrows for the EP direction have flipped. They flipped. Now, sodium has the two forces opposed. And look at potassium. Now potassium has both forces aligned. The engine of diffusion, which always points in that direction for potassium, is now being helped by wind, if you will. The opposite is true for sodium. The engines have always and will always want it to go into the cell. But in this case, the wind is fighting it. Why? Again, because we are now positive inside the cell. My question, which we just answered, is which ion has both forces aligned, i.e., pushing in the same direction, when the cell is positive inside? And we just answered that. Potassium. And chloride as well, but that's not relevant right now. When we were negative, which ion had the forces aligned? It was sodium when we're negative. Now that we're positive, potassium has the forces aligned. Great. Let's get back to this. So we're writing, and we get to stage 3 at, let's call it 40 millivolts. Two very important things happen at this point, at stage 3. Sodium channels close. And potassium channels are finally fully open. So at stage 3, sodium is no longer coming in. Mom stopped sending you money. If mom was sending you sodium dollars, the sodium channel mom shuts, says no more. Simultaneously, you're spending potassium dollars really fast. In fact, this is the highest rate of flow, meaning potassium rushing out of the cell, that we ever get. So if we think about the bank account analogy, you're at $40. Yay, but you're spending like crazy. So what happens to your bank account? And you head right back down towards the resting state. Now, let's talk about stage 4. This is not very well labeled. Let me see if I can do this for us. Stage 4 is referring to the entire period between stage 3 and 5. So between positive 40 and negative 60. Stage 4 is not talking about this particular period. It's talking about the entire drop from positive 40 to negative 60. What's happening at stage 4? At stage 4, we have a couple of things. K plus is rushing out, hence hyperpolarizing. And sodium channels are in a refractory period. This means they can't open. Impossible to open. Because, and this is actually pretty simple. How do you open a sodium channel? You cross the threshold. So you go from negative 61 to negative 59. So you cannot go from negative 61 to negative 59 until, boom, this point. I can't think of a better analogy, and I don't like this analogy, but it's the only one I could think of. It's like firing a gun that shoots out flowers. So this flower gun, you pull the trigger, poof, roses. Now you pull the trigger again without releasing? No. You have to release, release, release until click. And that click is when we cross that threshold so that we can pull the trigger again and shoot off another action potential. Therefore, you cannot get an action potential at this point. Cannot do it. The fastest you can shoot off another action potential is that point. Does that make sense? I hope it does. So that's why uh, uh, the sodium channels are refractory. It's just really mechanics. All right, stage 5. The message goes out for potassium channels to close. You know what? We can add here sodium channels close at positive 40. Potassium channels close at where? Negative 60. I should say begin. Begin. Begin closing. See, potassium channels, remember I said they're slow. Slow to open and slow to close. While the message goes out for potassium channels to close at negative 60 at stage 5, they don't fully close until stage 6. So it takes them just a little bit of time from this point to this point to fully close. And that's why we have this post-action potential hyperpolarization. You see, because the potassium channels stay open a little bit too long, a little bit too many potassium channels leave, causing a little bit more negativity than we actually need, which is rest. That excess potassium that just left the cell, this is the axon. We have potassium here. Normally we have a lot of potassium here. And we just released excess potassium. And that's why we're hyperpolarized. But pretty soon, these molecules will diffuse away, dissipate, and our voltage will tick, 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 right back to rest. And that's the story of the action potential. See, once you hit the threshold of excitation, as I said, the rest is pre-programmed. Why? Because the channels are genetically programmed to open and close at these zones that I told you. Just for completeness, when do when do potassium channels fully open? They fully open at positive 40. And when do they fully close? Let's call it negative 80. Okay? So potassium channel opening starts at negative 20 millivolts, and they continue opening, and then they're fully open at the peak of the action potential. Similarly, they begin to close at a voltage of negative 60, but they don't finish closing until a voltage of -80. And that excess potassium leaving is what accounts for this portion, the post-action potential hyperpolarization. Then how do we get back to rest? That's this little picture here, talking about the excess potassiums that leaked diffuse away, and we get back to this situation with these particular concentrations, and everything is back to normal. Finally, just this quick one. This is just showing you the action potential here. We know that shape very well now. And it's showing you the timing of the opening and closing of sodium and potassium channels. Showing you that sodium channels open first and are quick, potassium channels open later and are slow.